This is slide number 18 and I am your presenter Asloob Mudassar. In the previous slide we have written down del square operator for the Cartesian coordinate system, spherical coordinate system and the cylindrical coordinate system. Now we have given their expressions. We have used del square in the wave equation. So the first row is the wave equation in the Cartesian coordinate system. The second mathematical equation is the wave equation in the spherical coordinate system. And you know that here we have retained only the radial part of the del square operator, because our wave function depends only on the radial part in this case. And similarly for the wave equation in the cylindrical coordinate system, the third mathematical equation, there we have also taken only the radial part, because the other parts are not contributing towards the wave because they are constants. So these wave equations has to be solved in order to find out the wave equation, that is psi. Now we turn to very important things, that is the Fourier transform of two-dimensional objects. The Fourier transform, as we have mentioned earlier, for example, that is a very important tool in order to analyze the optical system, that is the Fourier tools. So Fourier tools, one of the main tools in the Fourier optics is the Fourier transform. And here you know that O of x and y represent amplitude and phase transmittance function of the object. And e to the power minus iota 2 pi within the bracket fx into x plus fy into y is a plane wave that illuminates the object. So we can say that the field just before the object is equal to this plane wave, that is e to the power minus iota 2 pi fx into x plus fy into y. And the field just after the object will be equal to the amplitude transmittance of the object, that is O of x comma y multiplied by the wave passing through it, that is e to the power minus iota 2 pi into fx x plus fy into y. So you know that now we have written down the two expressions, very important expression. One is the field just before the object and the second one is the field just after the object. And here iota is actually minus 1 square root. And one set of fx and fy actually represents one plane wave. Now writing down the plane waves, for example, if you want to illuminate the object normally, that is you want to make the plane wave incident normally on an object, then you can choose fx is equal to 0 and fy is equal to 0. So the expression e to the power minus iota 2 pi into within the bracket fx is equal to 0 multiplied by x plus fy is equal to 0 multiplied by f. Actually this is a plane wave that has a unit amplitude and normally incident on the object. Or you can say that it is incident on the object in the direction of fx is equal to 0, fy is equal to 0. And if you want to illuminate the object with a plane wave, making some angle in going some other direction, not normally but at some direction, then you can say that we can write e to the power minus iota 2 pi fx into x plus fy into fy is a plane wave of unit amplitude incident on the object in the direction of fx comma fy. So you see that we have earlier related in one of the previous slides we have related fx and fy with their direction cosines, that is fx was equal to cos alpha over lambda and fy was equal to cos beta over lambda, where cos alpha where alpha was the angle that the propagation direction of vector of the wave makes with the x-axis, and beta was the angle which the propagation direction of the wave makes with the y-axis. So we can choosing fx and fy, we can choose the direction of the plane wave to illuminate the object. So this is the end of slide number 18.